Jim, thank you very much. And ladies and gentlemen, let me say what a great pleasure and even more what a great honor it is to share the podium with all of this distinguished group and also the amazing talk we just heard from Craig Ventnor. The answer, in short, to your question, can systems engineering at a global scale make sustainability possible? The answer is it's the only way to do it. But we're not close to doing it yet. We live in an age of technological breakthroughs that are profound and political confusion that is also profound, and almost breakdown of political leadership and capacity in government. The realities of unsustainability have outstripped politics. Our governments neither have the scale, the financing, the means, the knowledge, nor often the interest in facing up to these problems. So we have a profound systems challenge. We also have a juggernaut of a global economy that operates with inertia. And inertia doesn't mean sluggishness. Inertia means, in this case, tremendous growth of about 4% per year on the global scale, meaning a doubling time of the world economy of less than a generation, meaning that the pressures on the Earth's natural resources are proceeding so rapidly that they are beyond normal political and infrastructure time horizons. So we have a challenge that is, in my view, unique, unprecedented in scale, unprecedented in spatial scale, population scale, political scale, and temporal scale in the timing that needs to be done. We often hear about the miracles of science and technology and what they can mean in the genome or synthetic biology, and all of that's true, but it will not reach a world population in solutions if we are not a lot more clever about some fairly basic problems that we confront. So first, I use the phrase sustainable development rather than sustainability to emphasize that we're talking about environmental sustainability alongside economic development. Economic development is surely the most powerful political imperative on the planet because 6/7 of humanity live in developing countries that want to be like developed countries. And to give you the scale, developing countries have an average income of about $4,000 per capita, developed countries of about $40,000 per capita, average global income about $10,000 per capita, 7.2 billion people, about a $70 trillion world economy. And if the developing countries were to, quote, catch up with the developed countries, and they have the means to do so because it's basically through education, infrastructure, and technology that they will do so, that would mean mechanically a rise of income fourfold globally to, say, 280 trillion. Add in population momentum, which will carry the planet perhaps another 40% population increase before stabilization. We're talking about a 5- or 6-fold increase of throughput. Well, our current technologies cannot begin to do that because we will reach crucial planetary boundaries, ecological and resource boundaries, well before that happens. One answer to that is the growth won't occur. Countries will remain trapped in a highly unequal world, zero-sum struggle, fight for natural resources, fight over water, environmental refugees. If you think that's science fiction, that's our daily newspapers, ladies and gentlemen. And it will get worse. Or we find a way to engineer our way around some of these bottlenecks, and we know that that potential exists. The world could be run on renewable energy alone. The world, in principle, could be run on a pretty small square of the insulation of the Sahara Desert alone. That's not news. That's just basic physics. And that means, in principle, putting aside the 1,000 absolutely real practical problems, There are solutions, but we're very, very far from mobilizing them in the time horizon that's required. So I use the phrase sustainable development as the advisor to the Secretary General. This means three things in the formal jargon. It means economic development, including and especially the end of poverty. It means social inclusion for more equal societies, and it means environmental sustainability. We're nowhere near close, ladies and gentlemen, to achieving this. There remain about 1 billion people whose life is a daily struggle for survival. A mosquito bite, a heat wave, a temporary drought kills millions every year when you add them up. We have high and rising inequality and I would say lawlessness in our societies. We've invented a system of systematic lawlessness. They're called tax havens, among other things. Trillions of dollars are in the British Virgin Islands, the British Cayman Islands, British Bermuda. Thank you. You have created quite a system. It's inventive. It's incredibly destructive. It is under the political choice of this country and of others, because we have our own that we've created, to get this lawlessness under control. We have massive degradation of the climate in all parts of the world, and we still have rapid growth of population. If you believe that population is under control, look at the situation in sub-Saharan Africa. The 2010 estimate is 856 million people. The medium fertility forecast of the UN Population Division is 3.3 billion in sub-Saharan Africa by 2100. The third most populous country in the world in the 2010 UN revisions as of 2100 would be Nigeria, 750 million people. My advice is don't try it. To go from 150 million to 750 million in an age of climate change would be nothing but disaster. But that's the trajectory that we're on right now. So we are not on a sustainable development trajectory. That's New York City, the pride of global capitalism, with the Hurricane Sandy in early November, in the midst of a presidential campaign where climate change wasn't mentioned even once, because our political system is so corrupted that we don't even talk about the most important things in a year of the hottest instrument year in American history, the worst drought in decades, a superstorm, but the politicians are terrified of the powerful interests. And so they don't even discuss these issues. But the other superpower, or the rising superpower, Beijing, it had the same floods. It has the same extreme events. This is worldwide now. Of course, while New York was flooded by Superstorm Sandy, we had a killer drought that covered 60% of American counties this past year and destroyed about 20% of the grain crop in the heartland of America, which is also the heartland of world grain production. And you can see from the summer this extraordinary drought. The dark red is exceptional, the lighter red is extreme, and the beige is severe. You can see that this was absolutely an extraordinary occurrence. The Farm Bureau, on the record, says there's no such thing as human-induced climate change. So it's also a very weird country, driven by many powerful vested interests and massive political confusion and massive ideological confusion as well. But it's not just the U.S. I spend most of my time in places like this, the poorest places in the world. They're already suffering extreme events that claim massive lives and that are at the core a major part of the violence and instability in places like Mali. I don't care how many drones we throw at the problem. We will not stabilize Mali, Somalia, Yemen, Afghanistan, or any place else when people are hungry. And people are increasingly hungry in these places. And our generals and our politicians don't get it. They just want to knock off the next al-Qaeda lieutenant as if this is going to solve anything. If we don't get to the root of the problem, we will not achieve national security anywhere. This is a map, I don't have time to explain it, of James Hansen, the chief scientist of the US government on climate change, looking at the 3 standard deviation events in the world, measuring 3 standard deviations on a baseline of 1950 to 1980, and then projecting by the same metric the number of extreme events in recent years. The maps at the bottom are for 2009, 10, 11. You see the world is covered by 3 standard deviation events, which are supposed to happen roughly 2 times out of 1,000, but are now happening 100 times out of 1,000 if you keep the 3 standard deviation metric of a baseline from 50 to 80. We're in the age of the Anthropocene. We're already in the age of instability. And the world knows it. Only the politicians deny it. You can tell I'm not too keen on our politics these days. I work in a lot of conflict-ridden countries. The drylands are our canary in the mine shaft in the world. The drylands are in drought. The drylands are suffering from instability because they already have the highest coefficient of precipitation in the world, and they are bursting out in conflict in a zone of about 11,000 miles from Senegal to Afghanistan. And this, I tried at the White House, I've tried everywhere. They cannot hear this basic message because it would force them to think. And there's no time to think. They always have an election coming up. But we are not solving these problems. This is what unsustainability means. The red triangles are the conflict zones. The colored areas are the drylands. We have choices. The world population is on track to reach more than 10 billion people by the end of this century on the medium forecast. With unchanged fertility rates, by the way, it would reach 16 billion. That's not going to happen. With a low fertility trajectory, which is in reach if we would help girls to stay in high school, basically, in poor countries, we could stabilize at about 8 billion and have the population come down to about 6 billion. This is a matter of girls' and women's empowerment. Of course, family planning, child survival, and especially secondary education for girls. But we don't make the choice yet. And it became politically taboo to talk about population in the world, especially for a lot of reasons. I don't have time to dwell on it. But we have to talk about population because nobody's aspirations for sustainability or sustainable development can be achieved if Africa remains on a trajectory of 3.3 billion people by the end of the century. Impossible. Asia, of course, will dominate in many of the crucial areas of resource use. It's China's rise that is the biggest mover of all of the major challenges right now. That's not to begrudge China its rise at all. In fact, on per capita terms, China is still roughly a half to a fourth of the U.S. and the high-income world. It is just to say China is big, growing rapidly, voracious in its resource demands, and with profound effects on all global markets, on CO2 emissions, and indirectly on deforestation, species extinction, and many, many other phenomena. That's what happens when a giant arises and grows at a rate of roughly 10% per year for 5 doublings over a 32-year period. And so we've had a phenomenal period of unprecedentedly rapid economic growth. That's good news. I'm a development economist. I love to see that. But we have planetary boundaries that are not being respected. As of 2050, about 80% of the working age population will be in Asia and Africa. So we should think about what this means geopolitically and how to organize around these issues. It's a major question. Now, very, very briefly, the world has tried 2 basic approaches to this, neither one totally satisfactory, but I want to propose something quickly in the end. In 1992, we went the route of international law. adopting 3 major treaties, one on climate change, one on biodiversity, and one on desertification. 20 years later, we met at Rio Plus 20 on the anniversary of the Rio Earth Summit. Nature magazine was correct to give these 3 treaties 3 Fs. Failures, massive failures. They have not shifted the needle at all. And for a lot of denial and geopolitical reasons, China says, we won't do anything till the U.S. does it. The U.S. is absolutely in the worst psychological hang-up about China, as well as in the grips of special interests. So there's paralysis in the U.S., and China says, if you're paralyzed, we're much poorer. Why should we do anything? And the rest of the world continues on. Europe is the only region of the world trying a little bit, even though it chose a very flawed model. This trading system was the wrong way to go on energy. You don't solve a deep structural systems issue by spot market trading of permits. It's absurd. It's just wrong idea. It worked if you trying to clean particulates out of a flue stack or scrub sulfur oxides. But the politicians who are not very knowledgeable in general and always looking for the easy way out took a long-term deep problem of energy transformation and said this is like cleaning smokestacks in coal-fired power plants of sulfur oxides, and took a flawed model because then they didn't have to use the word tax to put this whole mess in perspective. And so Europe is the only region that's trying to do something, but it chose a bad model. The rest of the world isn't even trying right now. And so the treaties failed. I've been involved in a different kind of exercise, which I believe in more, actually, or at least as a complementary part, and that is global social mobilization. As we call them, the Millennium Development Goals. These have been aspirational but not legally binding goals on fighting poverty, hunger, and disease. They've made a lot of difference, though by no means all that they could or should have done. They're not legally binding. We had no lawyers around asking what is binding, what's monitorable, and so forth, which has been what the climate discussions have been about for 20 years. Almost irrelevant questions, by the way, because the climate negotiators don't have a clue as to what's in their own country's real interests. I call it a poker game of 192 players, all of them holding blank cards, because they have no idea what their real energy systems could be like. They don't know what systems transformation is. They don't know whether they could run their power grids on offshore wind or on solar or on carbon capture and sequestration. What are they negotiating about? Only that someone else do something other than them. That's the only game they play. It's absolutely mind-bogglingly wrong-headed. The MDGs had none of that. They said, here are aspirations, let's get organized to do something. And I'd say they got halfway or even more in some areas. We need a global social movement combined with the systems engineering to show what can and should be done. The politicians will be the last to move. They are the followers. You, as engineers, are leaders, and you have to show what's possible in deep transformation, not in gimmicks, but to actually do the carbon arithmetic or the sustainable agriculture or the other areas. Politicians will not do arithmetic, ladies and gentlemen. They will not. So expertise has to do it first. I believe, as the Rio Plus 20 Summit adopted, we need to move to Sustainable Development Goals, SDGs, so that we should move from MDGs to SDGs in the UN jargon. What would these entail, for example? They would entail a commitment, which is achievable, by the way, of ending extreme poverty, because extreme poverty meaning not having even the basics to stay alive is obviously an anachronism in the 21st century. There's no reason for it. Targeted investments can end it. Second, it's possible that all poor countries could be at least middle income by 2030 because economic growth really works. Third, our societies could be a lot more socially inclusive, especially by ensuring that every child and every girl gets a decent, at least secondary education. This is the most powerful thing one can do within a generation. Fourth, we have to make a deep transformation to a low-carbon economy, to new, more complex, information-based agriculture, and to more resilient cities. And we need new norms for public and corporate governance. So that's my list of what the Sustainable Development Goals should entail. Let me just mention some of the technologies that are absolutely crucial for this. I would put the energy system as highest on the list. We cannot go on with the fossil fuel-based world economy, period. We probably don't even have the fossil fuel base because I think what we're finding is that many of the estimates, certainly the hype around hydrofracking, will not pan out. Even the vast presumed coal deposits are probably significantly exhaustible on the scale of the world economy at this point. So even from a resource-based point of view, we're in an odd situation of rising scarcity, rising real prices of fossil fuel, but enough fossil fuel to wreck the planet. So we're probably in the worst of both worlds. On the other hand, the breakthroughs in renewable energy are remarkable. We have photovoltaics now down to 70 cents a watt from about $50 a watt 40 years ago. This opens up actually grid competitive renewable energy in major parts of the world, but it needs systems engineering. There need to be transmission lines. There need to be smart grids to carry this. There need to be better ways to manage intermittent energy sources. So solar and wind really are vast. It's nice that wind is on the coasts, and that's where the world's major cities are also. So that's a pretty convenient fact, and recent studies of very detailed diurnal energy use on the east coast of the United States show fairly convincingly that the offshore wind could power essentially all of the northeast economy of the United States from Virginia to Maine. That's a huge fact, but we don't have one wind turbine out there yet, not a single one. We do have plenty of lawsuits over wind turbines, but we don't have a single wind turbine. We don't have any political leadership to actually break through these issues. So renewable energy, carbon capture and sequestration, I was asking just now, maybe we'll hear a bit more about it. Either it works or it doesn't work. There are major debates about this. If it does work, we can use fossil fuels safely. If it doesn't work, we can't. The amount of engineering on this has been far too small. There are huge open geological questions. Can you really store CO2 safely on a scale that makes a difference? Is this economically feasible? Should we forget it, as some people say, or is it real? And I see the heads nodding one way or another. I don't know. I'm just a lowly economist. And I noticed that when Craig Ventnor talked about his interdisciplinary team, he didn't mention economics on it. All the power to him. But the fact of the matter is we have to decide, we have to know better, I should say. Is that off the table or on the table? Because when I sit at the UN meetings, which I do, it's on the table, on paper. It's not in reality. It would be good to have a little bit more clarity of this point, I have to say, and I put a little bit in quotation marks. Of course, much smarter grids. Every scenario shows that we have to electrify transportation for the vast bulk of our transport. Almost any systems thinking says we need to go to electric vehicles on a large scale. So we need the generational change and innovation in that area. Agriculture, even more tricky, by the way, because there are 1,000 agricultural systems. There are only a few transport systems, but agriculture is local. It's local to climate, it's local to culture, it's local to soils, it's local to topography, it's local to ecology in many other ways. Highly complex, highly charged, massively confused. We have a great expert here, Calestous Juma, who I'm sure will say quite a bit about that. Cities I'd mentioned, population I'd mentioned. I think at a fundamental level, all of this is harnessing digital knowledge, which is our greatest advance. We are in the midst of a completely profound historical, technological revolution that I believe is as large as the steam revolution, as large as the electricity revolution, the knowledge revolution of computerization and Moore's law, and big data and transformations of biology, synthetic biology, engineering, nanotechnology, and all that this makes possible gives us the way forward to reconcile the aspirations of development and the imperative of environmental sustainability. Thank you very much.
Thank you very much, Jeff. I'd like to now invite Allard Castelein to come and deliver his speech.
Dear guests, ladies and gentlemen, after a potentially very transparent and daunting presentation by Professor Sachs, where fossil fuel are the destroyers of the world, I hope you will allow me to give you perhaps a slightly different perspective. I also will attempt to bring to you, as a community of engineers, the fantastic opportunity that actually presents itself in dealing with these phenomenal challenges we're all faced with, and the important role you as engineers actually have in this. But before we go there, I need to show you this disclaimer and to advise you not to make any investment decisions on what I'm about to share with you. You're a smart audience, so I don't need to read it out. Let me start. A couple of words of introduction, because I'm not so vain to think and assume that all of you know Shell with all its key facts and figures. But let me just summarize by stating that we're one of the largest independent oil and gas companies in the world, and that we do consider energy as vital in sustaining daily life, enabling progress around the globe. Shell's purpose is to deliver more energy in ways that are economically attractive and socially and environmentally responsible. We are a company of leading engineers that work on some of the biggest engineering challenges in the world. Last year, the company generated more than $23 billion in profit, and we spent more than $1 billion in research and development, largely on engineering solutions. And now the system deserts me. Engineering solution to get slides moving to the next one would be nice. There we go. You've heard before, and I don't need to elaborate, that more and more people throughout the world are improving their lives thanks to energy. They're traveling, they're working, they're warming their homes, they're cooking their meals, and they currently are plugging their various devices into electric sockets. And global energy demand, therefore, will continue to rise due to the improving living standards and population growth. At the same time, the world's energy supplies are harder to find and more difficult to produce. And the environment and social challenges are increasing ever and ever. So we aim to develop innovative technology solutions to deliver the energy the customers need in that social and environmentally friendly manner. And that approach aims to reduce our environmental impact. It aims to address the challenges. It does not dispute climate change. It does not dispute man-made effects in that context. And we do work closely with partners to address the challenges we're faced with. Now, why do I believe the energy system still needs fossil fuels? if you look at this slide, it tells you that the reality is that the rising energy demand will need to be met by all sources, renewable and fossil. It takes around 30 years, for a new technology solution to reach about 1% of the global energy market. And if you look at the kind of pinkish line that starts in 1970, that's the third from the left, that's the one for biofuels. It shows that it has taken the biofuels market, as similar to the wind energy market, about 30 years to reach that 1% materiality level. So during these 30 years, this new technology still needs to grow 1,000-fold to get from test to that materiality level. And so there, from our perspective, if you do accept that energy is actually an important source for growing prosperity and progress in the world, it does mean that there's no escaping that hydrocarbons will continue to dominate the energy mix in the next decades to come. And our assessment is that by 2050, it will still be 65% of fossil fuels. Now let me again reiterate, we are not saying that there's no role for renewables. To the contrary. Professor Sachs, anything to do with this? So how do we tackle this? At Shell, we believe that responsibly delivering cleaner and more reliable and affordable energy is the best contribution we can make in order to create a more stable world where economies can thrive. We address it by changing our mix. We produce more gas than any other international oil company in the world. And this year, in 2013, we will actually produce more gas than we will produce oil. We also help reduce the impact of the energy needs by being one of the largest and most important biofuels producers in the world. And I'd like to reiterate, this is grown in Brazil. It's water, rain-fed, so not competing for water with local populations. And the land in which the biofuel sugarcane is grown does not compete with land for food. From our operations, we indeed try to deploy carbon capture and storage because we do consider it an important contribution to curtailing greenhouse gases. And we look, of course, at our own energy efficiency in our own operations. Now let me then hopefully show you something which, as engineers, I hope you would be connected to and would find interesting. Some of the natural gas is the cleanest burning fossil fuel, I should say. When you use natural gas to fuel a power plant, the greenhouse gas emissions compared to coal will see a reduction from something like 50 to 70%. And like I said, if you connect it to a CCS facility, you could reduce the greenhouse gas emissions to 90%. Now, some of the natural gas is found in offshore deposits, far off, for instance, northwest coast of Australia. And a conventional field development with a subsea pipeline and a plant onshore would actually be too costly, hence not economic, or would have a significant environmental impact. So to develop these, Shell is building the first floating facility that not only produces and liquefies gas, but also stores and transfers LNG, all done at sea. And you can look at the dimensions, and you can see that that facility is a factor bigger than the largest aircraft carrier in the US. And I got a short clip here.
That is to build the world's largest offshore floating facility, which will be a game changer for the energy industry. From bow to stern, Shell's FLNG facility will be 488 metres, longer than 4 football fields, and will weigh around 600,000 tonnes, roughly 6 times as much as the largest aircraft carrier. Shell's FLNG facility will produce gas from offshore fields, liquefying it on board by chilling it to minus 162 degrees Celsius. This shrinks the gas by 600 times, allowing it to be shipped globally. Shell will be deploying this revolutionary technology first 200 kilometres offshore in Australian waters. The facility will be built at a shipyard in Korea and will be used to help open up new natural gas fields at sea that are currently considered too costly or difficult to develop. Its sheer size will help it withstand very high winds and giant waves. It's been designed to withstand the severest cyclones, those of Category 5. As a groundbreaking innovation, this will help meet the world's growing energy demand for the cleanest burning fossil fuel. Shell's decision to make FLNG a reality culminates more than a decade of research and development and 1.6 million man-hours. It builds on the company's extensive knowledge of offshore production, gas liquefaction, LNG shipping and the delivery of major projects.
Hopefully another slide should at some point in time come up. So I've shown you some of the challenges we as an industry are faced with. Now, this meeting is called Grand Challenges, and I suppose this is a nice lead into that we're also faced with huge challenges associated with what we call the energy, water, food challenge, or the stress nexus. Because as you can see from the slide, energy, food, water are very much linked. And if we continue to develop these opportunities, either in food or in water or in energy, along the traditional value chain thinking, then we're missing the opportunity and the stress it actually creates in that other important element, be it water, be it food. So we're actively working with other companies to address new and innovative ways to address these challenges, to come up with more resilient opportunities and outcomes based on the knowledge that we need to collaborate, we need to work together. Now I'm going to round off by showing you that it's not only engineering solutions that we should be looking for, and there's other opportunities that actually are just as powerful in the future world.
At the Nimmer oil fields in Oman, thousands of barrels of oil are produced every day. But only a tenth of the liquid brought to the surface is actually oil. The rest is water, which must be cleaned and disposed of. In the past, Petroleum Development Oman has pumped the water back underground, but this is costly and uses energy. A new approach uses reed beds to purify the water before it evaporates naturally beneath the desert sun. Using the new technique, most of the crude oil is first separated from the water. Traces of oil, however, remain in the water. Pulled only by gravity, the oily water then flows downhill through about 1.5 kilometers of reeds. As it passes through, the oil sticks to the reeds and is eaten by natural microbes living on the plant. By the time it reaches the bottom of the fields, the water is 99.5% pure and can be left to evaporate safely in the sun.
Die 4 Schilfkläranlagenstufen haben alles, was von der Ölproduktion noch übrig ist, an Öl entfernt. Auch die gelösten und im Wasser noch verbliebenen organischen Stoffe sind abgebaut worden durch das Schilf.
After a successful trial, the plant has been expanded to more than double its size. Engineers also hope that the process can soon be used elsewhere.
Die Vorteile liegen natürlich klar darin, dass so eine Anlage den Energieverbrauch für die Abwasserreinigung fast auf 0 runterfährt.
So to summarize, to meet the energy demand, we will need to continue to produce energy from all sources, fossil fuels included. Sustainable development is at the heart and at the core of everything we do. And innovation is in our DNA, and we need to collaborate to address these grand challenges of the future. Thank you very much.
Thank you very much, Allard. I'd like to invite Professor Angela Belcher now to the podium.
Well, thank you. It's a great privilege to be here today and be a part of this panel. I was asked to speak a little bit about my own research and what we're doing in making materials for energy and the environment. And the materials that we work on are really based on trying to understand how nature makes materials. I brought an example with me today, which is an abalone shell. It's a marine gastropod that's made out of calcium carbonate. It's 98% by mass calcium carbonate but 2% by mass protein, yet has really many fantastic qualities in terms of materials properties. But as a materials scientist, something that's even more interesting to me is how do you give genetic information to a non-living structure? And I'm going to tell you a little bit about that today. So I wanted to first thank my students. Everything that's done, I show you today, is done by my really fantastic students at MIT and in collaboration with many other groups. The goal of our research really is to give genetic information and give materials that haven't had the ability to evolve over time the potential to have some qualities like being able to be made under environmentally friendly conditions, be made at room temperatures and pressures, not use toxic materials and not add toxic materials back into the environment. And this abalone shell was made next slide. This abalone shell was made in the ocean about 500 million years ago during the Cambrian geologic time period. It took this organism about 50 million years to get really good at making materials. And we just had recruitment weekend for graduate students at MIT. And when I sell a project to a student, it's really hard for me to say, I have this great project, but it takes about 50 million years to get to the kind of material we want to be able to make. So over the last 10 years in my group, what we've done is we've tried to speed that process up. We've tried to find solutions to be able to give biology a new toolkit to work with many different elements on the periodic table, not just elements that they've evolved over this geologic time period to be able to make. And so when a male and female abalone get together, they pass on the genetic information that says, this is the code of how to build an exquisite material under environmentally friendly conditions. Here it is. Same with the diatoms that are shown in the bottom, glacious structures in the ocean that have the genetic sequence to build glass at ocean temperatures and build really beautiful different shapes. And so we focused on what if organisms had the opportunity to use more of a periodic table, not just calcium and phosphate and iron and silica. What if they could use other elements on the periodic table and they could also genetically code the synthesis of a battery or a solar cell in this instance? And so the work is really focused on simple organisms like bacteria and viruses and yeast, trying to convince them to use the rest of the periodic table and make a structure that we're interested in. I always say that we use simple organisms. I have a 2-year-old, and it's hard to get them to do anything that they don't want to do. But when you're working with simple organisms, you can convince them to start using other kinds of building blocks. And so in this instance here, it's how do you go from a DNA sequence to a self-assembling battery that's on the same has the same performance as batteries made under other kinds of conditions. And so we're interested in many different significant problems, energy, healthcare, and the environment. And to us, understanding how to control materials at the nanoscale, I think, could have a big impact on many of these different challenges. And so the idea is to take a small collection of atoms and control their crystal orientation, their size, their shape, and what's next to them. And by doing that, you can have a big impact in performance for solar cells and batteries and fuels, CO2 sequestration and storage, more abundant materials, water purification, therapeutics, and imaging. And I'm a material scientist, so everything to me is a material. And so if I'm making it for solar cells, I'll show you an example today. Materials that we made for solar cells, increasing the efficiency of inexpensive solar cells, are the exact same materials we're using for imaging ovarian tumors. And so going back to this idea of controlling materials on the nanoscale and how it works in biology, life has already given us a wonderful toolkit of molecules like DNA and antibodies and proteins and ribosomes that are already on the molecular level. And these are proteins and molecular machines in the body that can already control molecules on the nanoscale and can control inorganic materials on the nanoscale. And so we think it's a wonderful place to start to be able to put these ideas together for new kinds of functionalities. And if you look at materials that are already made in nature, there's a coccolithophore. It's a unicellular algae made out of calcium carbonate, already on the micron and nanometer scale. This abalone shell here that has nanometer scale tablets that stack on top of each other in a brick wall-like structure that are controlled at the DNA sequence. This organism has a DNA sequence that controls the proteins that control the structure. Same with diatoms and magnetotactic bacteria that make small single-domain magnets. And so the way that this works in nature is that organisms in the ocean have proteins. These proteins are encoded by the DNA. And these proteins have sequences that can grab atoms out of the environment. In the case of a shell, they can grab calcium carbonate, and start building up these inorganic materials. And so what we decided is, let's find an organism that can do the same thing for a semiconductor material, a magnetic material, or any material of interest. And so how do you do that? Again, I said we're trying to get past that 50 million year time scale, and so we do 1 billion experiments in the lab at a time, where we genetically engineer simple organisms to work with semiconductor materials and magnetic materials and different kinds of metal oxides. And it's all based on a bacteriophage, which you heard about earlier today, which is a virus that infects bacteria. It's an object that's 900 nanometers across and 6 nanometers in diameter, and it has the DNA sequences that code for the proteins that make it up. And so what we want to do is take that virus and have it learn how to work with battery materials or solar materials over a 3-week period of time, clone it, make millions or billions of copies of it, and then get it to work on materials that we're interested in. And it's all done through pretty simple genetic engineering, where you go in and cut and paste DNA sequences that code for peptide sequences. And so how do you get from a DNA sequence to a functional device? How do you do that manipulation? We do 1 billion experiments at a time, and then search through in a trial and error method to find the one that can build a better solar cell or the one that can build a better battery. And so we do it through a process of taking 1 billion viruses, force them to interact with any kind of material we want. We take the one out of 1 billion that works, and then we amplify it up and make 1 million copies. We go through this kind of process about 5 times, looking for the survival of the fittest, the one that can grow a better battery, and then we take that one and we can clone it up. And so the kinds of things that we've focused on. Oops. So the other idea is trying to put together 2 materials that are very hard to mix together. In this case, we're trying to put carbon nanotubes and nanoparticles together, and we do it through evolving the virus to do 2 things. One, pick up a carbon nanotube, and second, to grow a semiconductor material. And so we focus on, and this is a cartoon my students made of my collaborator, Paula Hammond. We want to give genetic information to solar cells, to batteries, to catalyst. I founded a company that developed catalysts that convert methane into ethylene and ethylene into larger based carbon chains for drop-in fuel replacement or for plastics. I have an example here of a yeast-based material that we evolved for the ability to take CO2 from a mock coal plant and convert it into building supplies. In this case, it's a green tile that's made biologically that could replace the flooring that you walked in on today. Another example is evolving structures that could find tiny tumors, 1 millimeter size ovarian tumors, non-invasively in patients, and then developing new photocatalysts for converting water or CO2 into fuels. This is an example of the battery. We've been working on evolving biology to make new anodes and cathode materials, and we've done this by. Here's 2 of my really fantastic students. They took a virus and they evolved it to be able to pick up single-wall carbon nanotubes. And then they had a second gene where they evolved it to grow at room temperature conditions iron phosphate material, and then have this biological structure self-assemble itself into a battery electrode. And here's an example of that battery right here. This is one that went to the White House because it was a very great battery at the time that we built it, that was built biologically, that was built at room temperature using non-toxic materials, and that assembled itself. Basically, the thing that was really interesting for us is that you could go through genetic engineering and you could find, you could make your batteries better and better as a function of time. And in the end, we produced, through several rounds of selection and engineering, we produced batteries that were as good as the state-of-the-art batteries at the time. We're looking at using that for other kinds of battery materials, going beyond lithium-ion batteries. We think biology has a role for that as well. Through selection and evolution, we've started evolving viruses for lithium-air batteries that are getting around some of the problems with cathode materials that are currently limiting lithium-air batteries as a material. We've been able to do the same thing with solar cells. These are dye-sensitized solar cells, which are inexpensive solar cells. We thought that biology had a place for increasing the efficiency of solar cells. The way that a dye-sensitized solar cell works is you have a dye, you shine light, you promote an electron. That electron is injected into titanium nanoparticles, then has to make its way through this random network to the current collector. What we decided to do was to evolve a virus to pick up carbon nanotubes, sit in there, and act as a direct connection to the current collector. And we did it through genetically engineering viruses to pick up single-walled carbon nanotubes. And then we put 0.1% biology in our active solar cell, and in 0.1% biology increased the efficiency by 33%. And so, in this case, a little bit of biology, selection to evolution, went a long way towards device performance. We use that same material that I described today to look for 1 millimeter tumors in ovarian cancer, and this is work that's done in collaboration with a medical school in Harvard. The surgeons use our new probe to look inside, it's in animals at this stage, to find tumors that they couldn't find without our probe. And in the last few minutes, I just wanted to say that we think that this technology could be important for fuels as well, and it's kind of a different kind of biofuel. In this case, biology creates a new catalyst, and that catalyst is involved in converting natural gas, which is a very stable molecule, into ethylene. And normally this is done through a cracking process where you take a larger chain molecule and you break it down into smaller pieces. But we think the way to go is to start with one carbon and add a carbon at a time. And so through, people have been interested in this problem for about 30 years, and through about 18 months of selection and evolution, we're able to find the catalyst that makes this possible. So that's, I'd like to thank you for your attention. Thanks.
Thank you, Angela. John Loughhead, over to you.
Well, good morning, everybody. I feel very comfortable being here. I'm an engineer. So when I'm in a group like this, it always feels good. But I would like to introduce you to a tribe that is a bit foreign to you, that works in my organisation, the tribe of psychologists and social scientists and behavioural scientists and other people, and make a very simple message as part of this. And I'd like to make that message in the context of the challenge that we face with regard to our energy system. And I'm going to do it in the context of the UK. And the message is actually on the title slide. So if you're tired, you don't need to listen to anything else. And it's all about, don't forget the people. If we look at what we're trying to do in the UK in terms of decarbonising our energy system, then the graph behind me shows the rate of change that we're trying to achieve. And what you will see is that it's very large. So we're trying to embark as engineers and politicians on a path of decarbonising very, very aggressively and ambitiously our society. We're trying to improve the future energy to gross domestic product ratio really faster than has ever been attempted before. And the message that I would like to bring is the fact that if we're going to do this, we have to make substantial changes on the demand and application of energy that we actually see. So when we look at a low-carbon future, we're going to need what engineers think of as energy efficiency, which is a technical change that improves the performance of the devices and systems that we use. But equally, when we do that, what do we find? Demand and consumption generally doesn't go down. People use the enhanced efficiency to have a higher quality of life in some way. So we need also some form of demand reduction, which will require a social and behavioural change that reduces the need for our services. We're going to need low-carbon vectors, we're going to need demand response, all the kind of things that we talk about as engineers. What I'm going to talk about is the outcome of a couple of colleagues of mine who've tried to answer these questions, which is what contribution to social changes need to make to delivering some of the technical changes that we're trying to improve, and what are the public attitudes to engaging with such changes. How does energy demand relate to what we're trying to bring about as system changes that Jeff spoke about earlier? And how much does that make a difference to actually delivering on some of the ambitions that we see as purely technical. So one of the issues that comes out is energy lifestyles, and it's very difficult to say what these are, but one of the things that we can say is that they apply to consumption, culture, social values, and many other things. And you can see this manifested very often in the way that people choose to live their lives. So if I can get the technology to work. And if we look at what happens in terms of households, there are various driving forces. We need to change the temperature that people use houses at, the way that they use lights and appliances, what choice of technology they bring about. And if we look at what we've got to do in transport, then we've got phenomenal changes to make in the distance that people travel, the choice that they make of the mode of travel, how they choose vehicles, and many other things. It doesn't matter what we do as engineers and scientists to deliver this, people have still got to choose to use it. I too am having trouble in getting the slides to change. There we go. And if we look at what the demand patterns that we might seek to achieve to deliver some of our ambitions, we see that they require quite dramatic changes in that consumption, even over quite short timescales. And if we also look at what impact that has on the way that people live, the graph behind shows how our residential fuels in the UK will need to change over the next 30 years quite dramatically from the current high consumption of predominantly gas and go down to much lower consumptions, probably of electrically driven systems or very high efficiency systems. Similarly, if we look at the impact on transport, we're going to need to change from very high consumption of diesel and petrol and go down to much lower consumption of those, but also the substitution, as we heard earlier, of things such as electricity. These are changes that many people don't know how to actually bring about. And I would point to all of you and say, who's managed to halve their consumption of fuel for their car, or has halved the amount of gas that they use in heating their house, or electricity in cooling their house? So the question that we've got to say is, if we provide all these clever solutions, is anyone actually going to use them? What are the public attitudes to those changes? And how do we understand how the public interacts? Now, we've been doing some studies on public attitudes, and I won't go through the detailed concepts, but what's underpinned those is that at the political and technical level, we've produced literally hundreds of scenarios over the last 10 or 15 years to say how we're going to change things. If we actually look at the transformation that we bring about, we're trying to change not simply an energy system, we're trying to change the underpinning values in the way that everybody lives their lives. And the uncomfortable truth, ladies and gentlemen, is we in this room are a small clique, a very small part of the world, and a lot of other people in the world do not have the obsession that we have with some of these things, or even necessarily a driver to employ them. And if you look at the things that will be impacted by what we've got, it's quite interesting. This is a brief survey to ask how favourable people are to different kinds of fuels and sources. And there are two surveys between 2005 and 2010. What's remarkable is that public attitudes don't change. People actually are in favour of things like solar, wind, hydroelectric and biomass, and generally against gas, coal and other fuels. So one of the things that we've done is actually gone out to look at these scenarios with people in groups and say, so you're very much in favour of it, are you going to do it, and how are you going to do it? And to do that, we used a modelling system that exists in the UK, which enables you on a computer to actually look at how you modify the supply of energy, your demand for energy, your lifestyle, in order to bring about certain decarbonisation targets. And that was the underpinning part. And what came out of this, and I'm now at the message that I would like to leave you with, is that in looking at this and talking to people, not experts, the thing that comes out is that, first of all, we need to explain what we call the whole system framing of this problem. Most people do not understand why they're being asked to pay more money for different forms of energy, or why they're being asked to travel different distances or use different modes of transport. When it comes to some of the key questions, the other thing is that what is termed the public interpretive frame, that is, the way that people think about these, are totally different to that used by most policymakers. People do not think in terms of pence per kilowatt hour. They don't see any straightforward relationships between these big meta issues and the grassroots views about the needs and views on the changes in the energy system. But underpinning it all, there is an enormous positivity, we found, in enthusiasm towards change and a move towards a sustainable system. And one of the things that we also found, that in spite of that positive nature, the interventions introduced by government leave people quite vulnerable. They see that they're being asked to make changes that they've had no part in the decision-making process on, that they're being asked to take risks in changing the way that thing goes, and that the options offered to them, the trade-offs, are not really valid for their particular lifestyle. And so one of the findings that we come out is that when we're making these transitions, we have totally failed to involve the people that have got to make the changes that we wish to see. That we're not looking at the siting, we're generally not looking at the cultures and the social backgrounds of people, and that many of the issues that we have been trying to push, such as passive demand management, is seen as intrusive on people's personal lives and not giving them the chance to do something about it. Cost concerns are quite complex. It's not just about higher bills. They want to look at what are they getting from it, what are the transitions that they're enabling, and how much room are they having to do it. So the final comment that I would like to make is that in bringing about some of the changes that we're talking about, we need to bear in mind that there's a lot of people out there that we need to involve in it. We've got dramatic changes to make in energy demand. We've got dramatic changes to make in resilience. We cannot do this ourselves as engineers. And one of the issues that we need to face going forward is how do we engage those that for decades have not been engaged. Thank you.
Thank you, John. And so we come to our final speaker of the session, Professor Calestous Juma.
Thank you so much. I'm very grateful to the three academies for giving me the opportunity to be here. I actually had a proposal based on the quality of the audience that we can just declare the conference a success at this moment and ask people to go and have lunch. What I really wanted to offer in regard to developing countries is a positive message of the opportunities that exist today that make it possible for developing countries to make the sustainability transition. And there are basically two of them. One is that it's easier to do new things in places where you don't have incumbent industries. And so you can start from scratch in most developing countries. Secondly, you have the benefits of being a latecomer, in that latecomers inherit large stocks of scientific and technical knowledge, which they can put to use, which also means that they can actually do that fairly quickly. And those combinations, in fact, in my view, have not been expressed adequately in the area of public policy, but also in terms of the engineering community of thinking about where it might be possible to start doing some new things. And so I'm very interested in exploring this area of exponential growth in scientific and technical knowledge, and to see the extent to which this can really make a big difference for for developing countries. And we do have some inspirational models that actually explain this. You can go back and look at the ethanol revolution in Brazil, but we have other examples that are actually quite instructive at the moment. One is the area of mobile phones. For example, when the first mobile phone developed by Ericsson in 1956 weighed about 42 kilos. You couldn't use it to send text messages. Just because of advances, this has become ubiquitous. And we see really this happening actually fairly quickly. We know the story of mobile phones, but the next revolution is in fact going to come from broadband, the adoption of broadband technologies. That is really, if we take Africa as an example, this is what Africa looked like in 2009. The entire eastern coast of Africa didn't have any connection to undersea cables. This is what Africa looks like today, literally in 4 years. This is roughly $5 billion investment in cables. But what this map doesn't show you is terrestrial wiring, most of which is going to rural areas. That is going to have a huge transformational impact in extending the information revolution to rural Africa. There's roughly $8 billion of terrestrial cables installed just in 4 years in Eastern and Southern Africa. And this is triggering a new development that we hadn't really anticipated. Until recently, we thought that the only thing that African countries could do is participate in the development of software. We didn't think that there was actually capacity there to develop hardware that is adapted to local conditions. And this is mostly in transitioning from just mobile communication and starting to think about new areas like mobile education. And suddenly we see devices like this being developed by African countries. This is a laptop developed by young engineers in Mauritius. And now if I was looking for a place where there might be breakthroughs in new laptops for educational purposes, I wouldn't be looking in Africa. But that's where stuff is starting to happen. And I'm offering these examples because they have huge implications for sustainability. If you think of the connectivity that exists in Africa now, you couldn't achieve that connectivity using traditional landlines without having a massive increase in the ecological footprint of communication. And so advances in science and technology and engineering, in fact, are making it possible for developing countries to leapfrog into new areas and actually to be able to do it fairly quickly. Another example of this is the controversial one, which is the area of genetically modified crops. When these crops were introduced, at the beginning it was argued that they will never benefit developing countries. As of this year, 52% of the hectarage of genetically modified crops are in developing countries. And the growth is going to be in developing countries. And what we see, which is really interesting, is not just adopting existing traits. It's in fact developing countries, African countries, starting to invest in research to develop crops that address local conditions, particularly pest resistance, stress resistance, water efficiency. These are examples of activities going on in places like Uganda and Nigeria and others with very little involvement of foreign enterprises. Most of the work that's being done, for example, on controlling banana wilt in Uganda is all funded by the public sector in Uganda. So we start to see a shift, in fact, in the use of these technologies to solving local problems with huge implications for sustainability. Nigeria spends something like $500 million a year importing pesticides to control the pest that destroys cowpeas. That would be saved if they eventually start commercializing a variety they have developed on their own in one of their research institutions, actually one of their universities. And so these advances that we are seeing, we've seen the work that Craig Venter has done with the sequencing of genomes, that just makes it possible for African countries to do things that they could never have done in the past. We're starting to see new areas, interest in new areas, particularly in the area of material sciences, either with the water-absorbent polymers or water-repellent polymers that are being now tried out in various African countries. And again, it can be done, we've seen it's been done very quickly. We had, just beginning of this year, the establishment of a polymer research institute at one of the Kenyan universities. This was a product of 6 months of discussion with a very small country, Slovenia, 2 million people. And so we're starting to see leadership, in fact, in the sustainability arena, coming from small countries, not the major countries. And so this opens up for me really a new way of thinking about where partnerships might actually come from, that may not come from the traditional large players, but most likely flexible countries that are committed to certain areas of partnerships. And finally, it's really going to be driven, in my view, by a greater focus on the youth, particularly in the developing countries, partly because of the age structure, but even more importantly, because the enthusiasm that the young people in developing countries have for science, technology, and engineering. And finally, we are starting to see the emergence of leaders in these countries that are dedicated to using engineering for development. Just last year alone, 6 African countries elected engineers as president. And I don't think this is a fluke. I think the challenges are starting to select for leaders who actually understand how to use science and technology to solve problems. So I wanted to leave you with that as a message, and I look forward to your questions and comments. And thank you very much for your attention.
Thank you very much. Okay, so we're going to move into a Q&A session. I note that we have eaten over a quarter of an hour into this, and speaking of eating, I don't want to deprive you of your lunch for too long. Can I just first ask the panelists to all shuffle forward so that the front row see more than just our somewhat shiny, in some cases, heads? And also to ask the questioners in the audience, when the microphone comes to you, could you please hold it close to your mouth, because we've received a message from, I think, the group in Birmingham watching this event that they can't quite make out some of the audience questions. But okay, so let's have some. To our first questioner, yes, gentleman there, and then we have another one. Either one of the raised hands. I really don't care. We'll come to both of you.
Yes. E.B. Friedman, University of Rochester. I heard a theme. What I heard from Professor Sachs was a kind of a macro model about standard of living. From Dr. Loughhead, a micro model of standard of living. I hear that China wants to have a higher standard of living. I hear that 6 billion people want to enjoy their standard of living. Nobody wants to change. So how do we convince all these people to change their standard of living, lower their standard of living, to be honest, is what I hear. That, to me, is the theme of the whole panel.
Well, who would like to address that? Either of you gentlemen to my right, or do you? Yeah, Jeff.
Just a word. I'm not sure that it really is lowering the standard of living in a meaningful way. To the extent that we shift to more sustainable technologies, which can outcompete some of the heavy resource-using technologies, we can have a higher quality of life, save the planet, and not really deprive people of crucial things that they need. Better education, better health care. A lot of the technologies are going to allow us to do more with less footprint on the planet. And I think that really is should be our way forward in this. It isn't only to restrict. Probably with smart grids, smart vehicles, smarter applications of these technologies, things that really count for people in terms of quality of life will improve.
Did anyone else want to add to that? John?
Very briefly, think one should not underestimate the challenge of making these changes, and I'd suggest that it's going to happen in phases. And really, the point I was going to make was the first phase is that we need to engage the rest of our countries in the kind of things that we see as obvious and necessary, but many people don't even recognise as something that they should be engaged with.
I have a second question.
Hello, I'm Jared Dunman from Oxford University. I had a quick question, probably directed more at Professor Sachs and Juma, but whoever, of course, wants to chime in. You both mentioned the role of engineers in different ways in politics. Professor Sachs lamenting the inability of some politicians to understand very complex engineering problems and address them appropriately. And then in the developing world, Professor Juma talked about how 6 African countries now have engineers as president. I'd be interested in your thoughts on the best ways that engineers can and scientists really can impact the development of society and addressing these challenges through engagement in the public sector, and how that relates to current and traditional emphases in engineering education.
I think that in addition to the actual engineering that we've heard a lot about, one of the things that is absolutely vital is to help the public, and through the public, the politicians, understand what's possible. We've debated, for example, climate change in the United States over 20 years, mainly around the issue of cap and trade. This is the least useful entry point to this discussion imaginable. What we have not had are scenarios, just like the UK ERC has been providing, of what this can really mean. We don't have the backcasting. Here's where we need to be in terms of carbon. What are the pathways that can get us there? Governments are very poorly equipped to do that work. Surprisingly, very disappointingly to me, governments that are poorly equipped have not asked engineering societies to work on it. The UK has developed an institution exactly for this, but we don't have that, for example, in the United States, and the vast majority of countries do not. So very few countries, and I'll put the US on that list, very few countries have scenarios that can help the public to understand what these issues are about. And I think engineers, not alone, but together with other communities of knowledge and practice, can help make those scenarios so that we can understand why this is a transitional period. It has to be. From a mechanical point of view, I would say, it has to be a transitional period to something different. And the public has very, very little appreciation of that, and the politicians have not helped at all, because they've been debating legalisms, or they've been debating mechanisms. They've not really been, and they don't understand themselves, understanding what pathways, critical systems pathways of change might be. So I think there is a huge role to play here in that specific regard. The other role is to help make these technologies real and effective.
Angela, do you want to come in? Then I'll come to you, Calestous. Yeah.
Well, I think I agree completely, and I believe that our jobs as engineers is one of public service. And so it's not only being in the lab, developing new products, and it's also public speaking. It's speaking in your library, speaking in your local elementary school, and talk about what it's like to be an engineer, and what we're developing, and the impact it could have on people's lives. And so I think it's a public image, and I think it's a public service.
Yeah, I'm currently chairing a high-level advisory panel for the African presidents on science, technology, and innovation. And this in conversations with them, basically the one message comes through, that African politics is a footnote on poor infrastructure. It's transportation, energy, irrigation, and telecoms. Those are the things that preoccupy African leaders. So it's not a surprise that we are starting to see engineers, in fact, rising to positions of influence. The other interesting thing that is happening is that That's the answer to your question in regard to how to structure the educational system. It's a shift, significant shift towards experiential learning. And this focus, which is basically pragmatic training of young engineers, the area where it's most manifest, again, is in telecoms, which is most advanced. And we're starting to see the emergence of new telecoms universities in Africa that are not under the Ministry of Education, that is focused on issuing degrees, but they're in fact embedded in the Ministry of Telecoms that is focused on problem solving. And we have 3 examples in Egypt, Kenya, and Ghana. And there are a lot more experiments going on in other ministries with roads, basically upgrading research institutes within line ministries that have a practical orientation to become the new generation of institutions of higher learning. And now, again, this is something you can do a lot more easily if you are in a place that doesn't have a lot of universities. But if you have a very dominant universities that are defining what education looks like, it is much harder to do. It takes me back to my original point that you can do some of these things more easily in new places.
We have a question from up in the gallery.
Zach Reaver. Zach Reaver. I'm a 5th-year student at the University of Toledo, bioengineering and biochemistry. My question's directed more towards Professor Sachs. Well, first off, I wanted to make a comment about the desertification. I saw a TED Talk about using huge livestock herds to simulate natural herds that has actually reduced desertification. So it's an interesting one if you haven't seen that TED Talk. I also wanted to comment about the politics you said. I know even as a student at my university, trying to get fellow students to be involved with sustainability and things like that is incredibly difficult. I started this green fund, and just getting people to opt into that is very, very difficult, even if you explain all the benefits to that. Now, coming from the economist's point of view, I usually don't hear economists talking about these issues. I was curious what your thoughts are on about having a new model of economics that's not based on growth, because I think we're all addicted to the concept of growth. You still have to have it, obviously, but in the society of today, you have to have a new model that's not based completely on that, but managing what we do have. And
okay, maybe that's
good. Sorry.
A good question to stop there. Jeff, did you want to comment briefly?
Very, very briefly, economics as a discipline, taught in our universities, became a denaturalized discipline in the 19th century. So while it started with the physiocrats and agriculture, land rents, Ricardo, and all of that, by the end of the 19th century, it was a system of differential equations where nature no longer had a role. This worked rather well if you could assume an elastic supply of primary commodities and ecosystem services at fixed relative price. You could show by formal theorizing you could just exclude them. Now we've reached boundary conditions. The shadow value of these resources is very high and rising, if I could put it that way. So we have to renaturalize economics, and this is part of what is happening. Fortunately, tools like massive GIS and putting nature back into an economic framework is there, but also there's a difference. I'll just add one more point. Economics needs to become much more of a system science than it is. It is a market science right now, not science. It's a market framework, but markets are not the sum of systems. And we need a both renaturalized and a systems basis to economics. So this is going to be a change in the coming generation. A lot of my colleagues don't know it yet, but this will be at least what's being taught a generation from now.
Lots of questions. Okay, very, very briefly, I'd like to ask a question, Allard, maybe to you. I think you're the only person who mentioned nexus as the stress nexus: food, water, energy. Do you think that the issues of population and quality of life, and then environment are very often treated as very separate problems. And do you think that thinking is changing now at all?
Well, I do think it's changing. The question, of course, is it changing quickly and rapidly enough? And I suppose the one thing I didn't mention in context of the Nexus is that we're also faced with, if you like, the broken triangle of trust between businesses, governments, and society. So I think we all do wish to change. However, we're not clear how we should change and how we should collaborate to change. I do believe that companies, leading institutions, academia, should not, as we have in the past, perhaps in the run-up to Rio, the run-up to Copenhagen, been looking at governments. I think now is the time for companies, NGOs, academia to stand up and look for those new collaborative models, and then go to governments and ask for the necessary policies. So it won't happen by itself. We need leading entities, leading organizations to show the way, and then seek the support from governments. And I hope we will be fast enough. But yes, we have a long journey ahead of us.
Questioner there with microphone, yes.
Hi, Will Stewart, Southampton University. I'd like to pick up on John Loughhead's point, which I would characterise as the social engineering being as important as the physical engineering, right? And then look back to something Craig Ventnor said, which is the example of world fisheries, which is another shared resource, global resource, where the science is well understood, the engineering is well understood, and the social engineering has been a complete disaster. So what new could we do for the social engineering to give us a chance on the CO2 problem, even the economic engineering, perhaps?
No, John.
I can't give an insightful or detailed answer to that, but I think to recognise that we've got to do it and that we've not so far done it well.
Okay, I wanted to bring in a question. Well, no one else wants to jump in. A question from Birmingham. Interesting one. They'd like to ask the panel their views that since we may start to colonise Mars within 20 years, should we forget about the Earth and being sustainable and focus on Mars instead? That's rather ambitious. No. Okay. Anyone disagree with that? Good. Good. Thank you, Birmingham. So we have a question. Gentleman here, unless someone's already holding a microphone. Oh, okay. Okay, so let's have you first, and then you.
Subhash Mahajan, University of California, Davis. I never heard anything about air. If the human beings or any organisms have to live, they have to get oxygen. And how can you maintain the purity of your environment and the air? What are we going to do with it? And the whole session, I didn't hear a word about it.
Do you mean pollution?
Air, the pollution.
Right.
And that has to be taken care of, along with the development of all new developing societies. And I think it's a mistake to assume the developing countries will like to have the same standard of living as the Western Europe has. These standards will be tempered by the local culture and the local needs. I take India, for example. Most of India is temperate weather. You can manage without air conditioning. You can manage without lights, but it will affect the standard. This factor has to be considered in what standard of living the Western, whether they will copy the Western world. My assessment is not. They will have their own paradigm, will depend on the local conditions and the local cultures.
Calestous, do you have any response to that?
I thought that was a statement rather than a question,
yes,
so I'm not...
I guess so. Okay, good, thank you. So, yes.
Mike Spencer, Cornell University. I have a systems question. In the 80s, President Carter in the United States said 1/4 of our energy would come from renewables. Not coincidentally, oil prices were high then. Since that time, solar has made dramatic gains, but still is not available. Installed solar is not good enough without, particularly without subsidies. And now with the real or not real gas boom, it seems, and my fear is that renewable funding for solar will not see the same levels that it has in the recent past, which is not very high. How do you fight this economic driver and still provide funding for these kind of renewables?
Allard, do you want to address that?
Yeah, excellent point. I think one of the things that we've seen is that subsidies are great to incubate and start new activities, new technologies, but in the long run, it needs to have an economic rent in order to be sustainable. That's part of a sustainable future. And so one of the things that we believe in is that one needs to start pricing nature. You need to put a value on nature. You need to put a value on carbon in order to allow for cleaner mechanisms to have a sustainable future. So even with the huge increase in availability of gas, I mean, let's not forget a decade ago or so, the world anticipated that we would run out of gas in 20, 30 years. Current hypotheses and assumptions are that it will be there for another 250 years. So the world will not run out of gas because there's no gas, like the world did not run out of stones because there were no stones. So subsidies to incubate good, pricing nature, carbon, necessary in order to have a sustainable future for renewables.
Okay, well, lots and lots of questions, and I should say now I'm not going to be able to come to all of you, I'm afraid. So gentleman there with a microphone, and then we have gentlemen on the side here. And we'll try and keep it. So we'll have just one panelist answer each question, I think.
Thank you. Richard Tomasetti, Thornton Tomasetti, Inc. Concerning the standard of living again, going back to that, okay, shouldn't we be looking at really, as the gentleman said over there, what is that definition? If we keep going in the direction that the definition of standard of living is becoming more and more of an ownership society and having more and more material things, as opposed to maybe having more people happy and having more people having less suffering, don't we have to use the latter to really get into sustainable solutions?
Jeff?
Yeah, I can say just a couple words about this. There is a rather substantial and absolutely salutary movement to try to measure these things better and also look at the question of what's called subjective well-being. How do people assess their lives, the quality and life satisfaction? I think the points are generally the following. First, increasing material well-being as conventionally measured makes a big difference at the lower end of the income distribution, both within a society and internationally. Having electricity is a great thing from all points of view of quality of life. Having many of the benefits that are associated with a conventionally rising gross domestic product works. But one of the key, absolutely clear points is the declining marginal utility of income as conventionally measured, meaning that that extra 2% growth when you're already at $50,000 average per capita income, or why it is that our billionaires, as we read today, Mr. John Paulson, one of the richest hedge fund owners, $12 billion of wealth, wants to move to Puerto Rico to take advantage of a tax benefit. Really? There are not enough multiple lifetimes to spend that money humanly, physically possible in a finite body, even in a finite clan of all of Mr. Paulson's relations and probably everyone that he's ever met. So this is absolutely a psychological phenomenon of perversity in a certain sense as well. Now, to come to the bottom line, the happiest societies are the social democracies of Scandinavia and of Latin America like Costa Rica, which show that they come out at the top of the self-report. What does that mean? Good living standards as we would know them, but not the top, social equality, high quality of community, good public health. And in Costa Rica's case, no army. These make a measurable difference in the reported quality of life. In the United States, by contrast, in what's called the Easterlin paradox, named after Professor Richard Easterlin of Pennsylvania, University of Pennsylvania, the U.S. per capita income has tripled since 1960 without even a wiggle in the self-reported well-being in the United States. So there really is a very deep issue here. Why are we destroying the planet for something that doesn't even make us feel better?
Jeff, okay, I have to... Okay, well. We have, I want about now 2 or 3 minutes left for questioning. So a gentleman there with it was the microphone here, yes?
Tariq Durrani from the Royal Society of Edinburgh. Recently, Madame Bukova, the Director General of UNESCO, stated that to develop sub-Saharan Africa, there will be a need for something of the order of 2 million engineers in the next 5 years. I'd like the panel's views of how that can be achieved, and is there a role for national academies to assist in the development of such areas? And I want to link this thing to what Professor Calestous Juma showed, the development of mobile communications throughout Africa. My question to him is that sustainable, or is it only dependent upon government subsidies over the foreseeable future? Thank you.
Okay, so Professor Juma, maybe you can just respond to that last part of the question.
Yeah, one of the cables, the SEACOM cable that connects South Africa to Europe, it's a $160 million investment. 75% of that is from African shareholders. It's almost all of it is private sector investments. And that's been the most interesting part about these cables. It's predominantly private sector investment. So the argument that there's no money available in Africa, that African countries need foreign aid or they need the government to subsidize many of these activities is just not valid. And on your first question, I don't know how UNESCO calculates those figures, because I don't think they collect any statistics on engineers in Africa in the first place.
Thank you. Okay, so I'm going to try and get 2 quick questions in. So, a gentleman there, and then a lady at the back with her hand. She's been holding her hand up for a long time. Yes.
Hi, Zach Yima, mechanical engineering student at the University of Southern California. My question was actually very similar to the last one, but in developed nations, how are we going to achieve a smarter grid and overcome these different political challenges, such as you mentioned, Professor Sachs, and dealing with these politicians to upgrade the systems?
Anyone else want to?
I just wanted to say one thing about the engineers, and
okay,
maybe a word about this, which is that anybody with broadband, and that's going to be almost everybody, at least potentially with access, will be able to get the massive online open courses, as they're now called, the MOOCs. And we should be thinking about massive education, free, online, globally available to take on these challenges. I don't know what it's going to do for our business models and our home universities. I think in the future my lectures, I hope, will be downloadable at 99 cents a lecture on iTunes, but probably it won't even be worth 99 cents. And so I don't know exactly the business model, but in terms of making knowledge available, we are in the greatest moment of history for mass education. And it should basically be free, because the marginal cost is zero for another person to log on in their village on their 3G or 4G, which they're going to have because of the investments that Calestous was talking about. And if we can help to make sure that the contents there, whether it's 5 million or whatever number, will be available.
Thank you. Final questioner.
Hi, I'm Nikhila Ravi. I'm studying at the University of Cambridge. We heard from Dr. Venter about the cost of producing a kilogram of beef. It was like 15,000 litres of water and 10 kilograms of feed. So why don't we give dietary choices more consideration? Why don't we publicize that more when we're considering sustainability? It seems that we don't emphasize how much effect we could have by making good dietary choices.
Thank you. Who would like to be given the final word on this? John.
Well, I'll just make a very brief comment on that. My own organisation attempted to do this in the various events that we ran, and the response was complaints about the lack of meat. So my response, I think it's an eminently sensible suggestion, but I think, like many other things, it requires a long period of education and awareness.
Thank you very much, John. Well, apologies to those who haven't had the chance to ask their questions, but I think that the rumbling of tummies is starting to be louder than the questions. Ladies and gentlemen, please, once again, join me in thanking our panelists for a very enjoyable session. And if I can invite you all back to...